Given a linear system, you might wonder whether it can always be transformed to echelon form. And the answer is yes, it can. Gauss's method is always successful. Here's the theorem. Any linear system can be transformed to echelon form by row operations. Here's a sketch of the proof. First, the linear system might have all zero equations. And this is okay because it's already in echelon form. If instead it has a non-zero equation in some row, then at least one row has a term as far left as any other row. Okay, that might be in the first row or it might be in another row. If necessary, if that row with the far left term is not in the first row, we can swap it with the first row. So we have the first row with a far left term. Then in the column of that first row far left term, either all the terms under it in that column are zero or can be made zero by a row combination operation. That is, I can multiply the first row by some number and cancel off any of the terms in the rows underneath it. Okay, now let's look at the remaining rows. Among the remaining rows, the same situation holds. They're either all zero or at least one row has a term as far left as any other row. And this term will be to the right of the leading term of the first row because of the operations we performed in the previous paragraph. Now, if necessary, we can swap this row with the second row. And then the terms under its far left term are either all zero or can be made equal to zero by a row combination operation. So then this process can be continued. We can continue the remaining rows, find if they're not all zero, find a row with a far left term, swap it with the top row in this remaining set of rows, and ensure that that far left term has nothing underneath it. Eventually, we'll run out of rows, and the system will be in echelon form. Now, to make this sketch precise, we need to use a proof by induction. But this gives you an idea of why Gauss's method is always successful.